The next segment of the presentation is an open research in practice. We welcome questions through Slido, as well as direct questions from the floor. The first speaker of this segment is Associate Professor Roderick Bates from NTU School of Chemistry, Chemical Engineering, and Biotechnology. Prof. Bates is a fellow of NTU's Teaching Excellence Academy and the university's Research Integrity Officer. He has research interests in the use of transitional metals in organic synthesis. He is also a lecturer on forensic science for Coursera course. His presentation is about correcting the natural product literature through open data. Prof. Bates, please.
Okay, thank you very much. And thank you to the organizers, especially Suni, for allowing me to come and talk today. So I was thinking that a lot of the talks that you'll hear today are kind of very theoretical, giving concepts about open data. So I wanted to give a very practical talk to show how I have been using open data to correct mistakes in the natural product literature. And this is in collaboration with Mikhail at ACD Labs, Andre at the University of Denver, and especially Craig Williams at the University of Queensland. So first of all, let me convince you that natural products chemistry is important and that natural products chemistry has also made an enormous impact on human health. So here, for instance, is quinine that comes from Cinchona calisea. Here is penicillin, which comes from that mold you see growing in the Petri dish. Here's morphine, which comes from the opium poppy. And here's Taxol that comes from the Pacific yew tree. So natural products chemistry is extremely important to human health. And if you're going to use these molecules for health or for any other purpose, it is, of course, important that you know what their structures are and you get the structures right. So when natural products chemistry started in the 19th century, determination of molecular structure was done by color changes in test tubes and degradation studies, by chemical studies. And gradually, as instrumentation was invented, it changed to instrumental methods such as nuclear magnetic resonance spectroscopy. That's the machine you see there. For those in the medical school, NMR works on the same principle as MRI. So nuclear magnetic resonance spectroscopy can be proton NMR showing us information about the hydrogen atoms, or carbon NMR giving us information about the carbon atoms. And I'll also mention mass spectrometry and X-ray crystallography. So nowadays, structure determination is using these very, very sophisticated and advanced instruments backed up by tremendous computing power. But even so, there are still mistakes. Some of the mistakes are quite profound mistakes that you have to think about, possibly because the instruments are being pushed to the limits of their capability. And some of the mistakes, you see them in the journals and you think, how on earth did anyone ever publish this? So my first experience in this area was with a compound called asparagine B, which was isolated by my friend, Professor Wacharin, who is at the Prince of Songkhla University down here in Hat Yai in Thailand. Now in my lab, we are synthetic chemists. We make molecules. So when I saw Wacharin talk about this molecule at a conference, I told her, yeah, we can make that. We'll make that for you, and then you've got plenty of it for doing further studies. So we made asparagine B. Now, let me say a word about how chemistry is actually quite advanced in open data. We have had something called supplementary information for many decades now, which is basically all the extra data and the protocols and the methods. And it was started by the American Chemical Society, not for open data reasons, but to save money on printing. And it started so long ago that it was on microfiche, because it's before we had the internet. So Professor Wacherin, in her paper, in her supplementary information, provided the NMR spectra of her compounds. So on this slide, you can see the spectrum of our material at the top, the spectrum of her material at the bottom, and you can very clearly see they really don't match. So I wrote to Wacherin and told her the bad news. She was very good about it. She dug out her sample. She reanalyzed it with higher power machinery, and she realized, yes, they had made a mistake. What they had isolated was actually an alkaloid called prussine, which is a very similar structure. And the reason for the mistake, you see here all these overlapping peaks, which are not resolved with her instrumentation. And so this was a very nice experience because we could get their data, we could compare the data, and we published a paper together with the correction of this error. Not all experiences are so positive. So this is Afzeliindanone, which was isolated by a French group from a plant that grows in West Africa. And a team of 3 undergraduates, 3 FYPs, made this compound. The one who made it finally was Rita. And when she got her compound and she measured all the data, she was very disappointed because her data did not match the data reported by the French. But we were absolutely convinced we had made the right compound. We had made what's shown on the screen there. This is an X-ray crystallographic image of the stuff that Rita made. Now, Afzeliindanone was published in a journal called Natural Product Research, which is a Taylor and Francis journal, and it doesn't have quite the most rigorous of standards. And there was no supplementary information at all accompanying this paper. So we were relying on the numerical data which they had tabulated. So we couldn't see their spectrum, only their numerical tabulation. So this is where my collaborators, Mikhail and Andre, come in, because they have computational methods to work out structures from data. So they believe that is the correct structure. So we're going to make this, and then we'll find out if it's correct. But it's based on transcribed, tabulated data, not actual data. So we had to go back to the old method of getting the actual data, which is to write to the professor in Paris and say, please send us the data. So he hasn't replied yet. Okay. So here's another one from the same journal. This is a chemical that a group claimed they had isolated from red seaweed. And they claimed it was a COX-2 inhibitor, which is quite interesting. But if you look at this molecule, well, if I look at this molecule, then this is really unusual. It's not impossible, but it's unusual. And then when I look at this bit, that's really unlikely. Nothing impossible, but really unlikely. Now, they did publish some supplementary information. They did not publish the proton NMR, but they did publish the carbon NMR. And each of these lines here represents a carbon atom in the structure. Now, the bit in red, the bit that I think is unlikely, where are we going to find that in the spectrum? We're going to find it here, underneath this thing that they pasted in. So this illustrates a point that an earlier speaker made about the quality of the data. So looking at this, are there peaks underneath that thing that they pasted in, or did they paste it into blank space? I don't know. You can't tell from this. So again, I have to resort to the old-fashioned method of writing to the corresponding author. And so I wrote to the gentleman, and we had a very nice exchange of emails. But unfortunately, he didn't have the data. His student had the data. And this was what he said. Now, I have to commend this particular country for its very generous policies concerning maternity leave, because this is what he told me a year ago. And I still haven't heard any different. So quality of open data is critical. Okay, here's another one from the same Taylor and Francis journal, by the way. This molecule is also impossible. Okay, these substructures shown in red cannot be stable. And this substructure shown in red is perfectly possible, but does not occur in nature. Nature does not make that structure. But I'll tell you who does make that structure. Glue companies. One of those two tubes, I think it's the one on the left, has a chemical that contains that structure. In fact, that's the chemical in the glue. This is when you mix the contents of the two tubes to make the glue. Now, the organism from which they claim to have isolated this compound is actually a marine microorganism. So what I think they did is to culture the microorganism in homemade equipment held together by glue. And because it's a marine organism, you of course culture it in seawater. And what I think happens is that some chemical left over from the glue reacted with the salt in the seawater to give this compound shown here. So, very easy to test this, because this compound you can buy, you can then react it with some chloride, and you can get the spectroscopic data of the product. And once again, we can do the comparison with the data provided in the supplementary information. So this is my material here made from the glue. This is their material here. And you can see they really do match up very well. So we've been able to correct the structure, and we can also confirm that this is not a natural product. It is a glue-derived artifact. Okay, here's another compound. Now, just looking at this compound, it is not possible that this compound is stable. Not only do we have more than 100 years of experience knowing this compound cannot be stable, there's also good quantum mechanical reasons why it's not stable, and yet it was still published in Phytochemistry Letters, which is an Elsevier title. But we do have supplementary information. And this is actually my collaborator, Andre, who dived into this. And in the supplementary information, there is the mass spectrum, which gives you the mass of the individual molecule. And if you have the mass of the molecule to sufficient accuracy, you can work out which atoms are present in the molecule. And so these guys who published it, they recorded a mass of 257.1133, which corresponds to that molecular formula shown there, C14H18O3. And the good thing about having the data available to you is that you can take a close look, which is what Andre did. And there's that peak at 257.1133. But if you look carefully at the x-axis, you'll realize that's actually 251. How they got to 7, we have no idea. So it's not 257, it's actually 251. And then Andre realized that not only is that peak not with that value, it's also not a very significant peak. There's a much bigger one next to it at 273.1102, which corresponds to the same molecular formula, but one extra oxygen atom. Okay, so using his software, Andre predicts that the true structure is this structure here. So this is not a known compound. We're going to have to make it, and then we can do the comparison to see if this really is the genuine structure. But having the mass spectrum available through open data gives us this very important clue to what the true structure could be. So here's another fun one. This compound was claimed to be found in a plant called Morea Carnegii. And you should all be familiar with this plant. Some of you may have eaten some at lunchtime because Morea Carnegii is the curry leaf. So I've highlighted two parts of the molecule in red because these are obviously not stable. Those parts in red just cannot exist in the laboratory or in a plant. And then a few years later, the same compound plus an isomer were isolated from this fungus here. And this is really weird, to have compounds like this isolated from species that are so completely different. And fortunately, both of these papers, one of them from Elsevier, one of them from Taylor and Francis, come with the supplementary information so we can look at their data. So this is the carbon NMR spectrum that was provided with these papers. And this is the mass spectral data, which gave them a molecular formula of C9H17NO8. And if you look, there are 9 carbons. There's 4 over here, and there's 5 over here. 4 plus 5 equals 9. Except, what about that one? So because we have their data, we can see where their mistake is. Their mistake is in the molecular formula. It shouldn't be this one. It should be this one, which is actually got 10 carbons, which explains that extra peak there. And this molecular formula that you see here is actually adenosine. And of course, adenosine is in all living creatures. For those of you who know some biochemistry, adenosine is the A in ATP. So we believe that what they isolated is adenosine, and we can test that because we can buy adenosine, we can record our own spectrum, and we can compare it to their spectrum. So the green trace is our spectrum from commercial adenosine. The red trace is their spectrum. They're the same. This is the protons. And we can do the same for the carbons. And you can see it's identical. It clearly is adenosine. So this story we have written up. So we wrote a paper describing what I've just explained to you, and we submitted it to one of the journals that originally published the structure, and the managing editor replied, it falls outside the scope of the journal. So I think this is amazing. Correcting a mistake published by the journal is not within the scope of the journal. And this is a problem we have found. We can find and we can correct these mistakes through open data, but the journals are very unwilling to publish those corrections. Fortunately, in this case, we've appealed to the chief editor of the journal, and our manuscript has actually gone out for review. I think the problem here is that the mistakes are not only mistakes made by the researchers, it's also a mistake made by the journals. because it's a failure of the editorial and the review process that these errors ever find their way into print. Okay, so I hope, despite all the chemistry, you found this an interesting application of how open data can be used to achieve important scientific purposes. So let me once again just thank my collaborators in this project, Craig, Mikhail, and Andre. And then I just leave you this quotation here: "In God we trust. All others must bring data, and they should publish it openly."
Thank you so much, Prof. Bates, for the very interesting presentation. We have time for one question. Perhaps I can pick one from Slido. So the person asks, Prof. Bates, how do we ensure the quality of data? And is there any other better way?
How do we ensure the quality of data? You must never believe your data. I think this is the fundamental problem. People get some data and they're always looking at their data to see, does the data support my hypothesis? But that's the wrong way to do it. You should assume the data doesn't support your hypothesis until you can convince yourself otherwise. So you should always look even at your own data as a skeptic until you yourself are convinced. And then you will get higher quality data and higher quality interpretation of data.
Thank you, Prof. Bates. That was very, very insightful.